Hello everyone. Hi Manish.
Hello, sir. Good evening.
Yeah, good evening. Is my PPT is video is visible or not?
Yes, sir. PPT and video both are visible.
Okay, okay. Thank you. So let's wait for 5 minutes and after that we will start.
Yeah. Sir, first of all, happy Holi to you.
Yeah, happy Holi Manish.
Yeah. Uh, sir,
Yes,
actually, question is you are not from a chemical engineering background, and
yes.
whenever you are simulating in Aspen Plus, so you are not getting any difficulties in kinetics and kinetic equation and all that.
Because suppose if you have a problem with you, then
Hmm.
basically I'm working with system thermodynamics.
Okay.
So yeah, so I'm basically doing the using the Gibbs free reactor actually. I'm doing the reforming calculation and all, and
Mhm.
energy and exergy efficiency calculation. So I'm not basically in the distillation and all. So that's why I'm not in those reaction kinetics and detailed kinetics and all. Yeah.
Actually, I was asking because I'm not working in means a process engineering background right now.
Okay.
I'm into
Okay.
I'm into quality control, and it's been 3 years I'm working in quality. So I have forgotten many basic things, not basic things, but whatever the kinetic equations, their iterations, many things I have forgotten. That's why I was asking that if yes.
Yeah. Actually, yeah. It's really actually because it's basically connected to your problem. Actually, you don't need to understand every method because Aspen has very huge database. So you don't need to understand everything. So the
Right.
point is that in which area you are working. So you need to understand only that part. And now with the help of this course, I think you will be able to understand how you can use sensitivity analysis. You can optimize. How can you use different models? So now
Mhm.
basically you have introduction of all basic facilities available in the Aspen. Now as per requirement you can use that, and if you are in the kinetics, then you can refer some good book regarding the kinetics and that will be very helpful to you. But
Yeah, I
it's
can
not.
refer
Yeah,
reaction engineering.
yeah. But it's not mandatory that you should be aware of every aspect of the Aspen. I'm also not aware of every aspect of Aspen. So
Yeah, that's why I
I
was
yeah,
asking to you because
yeah,
the
no,
same
no.
question was Prabir Kumar sir. So
Yes.
sir said that no, you must be having knowledge of all these things. So I asked the sir, sir, what book should I follow? So sir told me that. Means sir told me two three book names, and that books was the similar books which we have used in engineering.
Yeah. So it depends on your domain actually, because if you are only working in particular area, so you should refer. If you are in the kinetics, then you should refer a book. For
Right.
me, I'm not in the reaction kinetics and all. I'm just doing the
Mhm.
system thermodynamics. So I'm my focus is on only onto that part.
Mhm. So it means after all, I have concluded that I will keep on learning the software things, and
Yeah,
whenever I need like kinetic things like heat exchanger design, then
yeah.
I can refer to only that particular section from the book,
Particular section. Yeah. Right. So
so
that's
that I will have
the
a good idea about that.
yeah. Because that's the main idea. Because if you are working on a particular problem, so you are not working on Aspen. You are working on your problem. So you should be
Yes.
more specific to your issue. Because Aspen
Mhm.
is huge software. So if you see the property only, so there are so many properties. So if
Right.
you go deep into that, then and the research is going on. So new
Mhm.
models are coming, new properties are coming. So it's huge. So it's
Mhm.
only depend on your work, your related area. So keep focus in that area only, and you should be aware of all the aspect of Aspen. That's important, because if you don't know, like, you can, the Aspen has this facility, you can use, you can manipulate these things, you can use the, like, these tools. So that's important. That's why this course is. So with this, you will have a basic idea, because we have, I think professors have covered so many case studies. So in those case studies, I think now we have covered around 10 to 11 case studies as of now, I think. Yeah.
Yes, yes,
Yeah. So in those case study, you can see. So we have used multiple tools, multiple blocks. We have connected them. So that's the thing. So you are, yeah. So you are getting, I think, a lot of knowledge from that.
yes, yes, right.
Okay. So let's start. So
Yeah. Thank you, sir.
good evening, everyone. I welcome you all to the Aspen Plus.
Good evening, sir.
Yeah. Good evening. Aspen Plus live session for the basic course for beginners. Now we are in week 9, and this is live session number 9. So the course instructor is Professor Praveen Kumar Shah from IIT Guwahati, and I am this course TA, Amit Kumar Sharma. So I also wish you happy Holi to all. Okay, so let's
Happy Holi.
begin. Yeah, thank you. So this meeting is being recorded, and the PPT that I am using in this meeting and the video will be shared to you from the NPTEL team. So those who are not able to attend today, they can refer to the video, and you can also refer to the class videos. Okay, so let's start. So briefly, first we go through the course summary. So in the week 9, professor covered 3 case studies. So the first was synthesis of ammonia in cryogenic process. Okay, so we will go through this case study after the discussion of the assignment questions. Okay, and this is the complete flow sheet of the case study. The second was regarding the production of cumin. And third case study was regarding the design, rating, and simulation of heat exchanger. Okay, so we'll go through these case studies after the discussion of the questions. So let's begin with the questions. So the question number 1 is, you have a heat exchanger and you want to know whether the equipment is fit for some desired output performance. Which among the following calculation would you do? Options: design, modeling, rating, and simulation. Think about it. Let me know your answer with the reasoning.
Rating, sir.
Okay. Anyone else? Okay, so what is your reasoning behind the rating?
So we need to do the rating so that we can find out the tolerances of the you know heat exchangers, and we can basically find tune the answers.
No, your answer is not fully clear. So what will be the difference? Suppose, what is the, like, why design is wrong? What is the meaning of design or
The,
simulation in this?
the design is like you have to start from beginning. So, but we have to we don't have to design. We have to check whether this equipment is suited for this performance. So design won't be there.
So design
Modeling
will
is
be
like
wrong. Okay, yeah. Modeling,
modeling is basically when you design the whole system. Like when you put things into process, that's called modeling.
yeah,
Modeling
yeah,
is
right.
also not. Rating is you need to put in tolerances and check whether this commercially available equipment is fitting our requirements or not. Simulation is we need to do simulation, but after doing simulation, we cannot get exact precise equipment. So from market, we have to find out equipment of a particular rating. So for that, we need to study the rating.
Yes, right. So like so basically the design, as we know, we are designing from the scratch. Okay, so everything we are designing in the design, and in the modeling, it's the complete process to connect different kinds of systems together. Rating and simulation. So rating, because you have a heat exchanger already. So now you have a heat exchanger and you want to check that is it your equipment is fit for the desired output performance. Okay, so basically you are comparing, the output, you are comparing your heat exchanger, like rating, is it like it is overrated or underrated. So you are doing that calculation. So it's rating. Simulation, you are simulating a system to get the desired output. Okay, so this is the simulation. So the answer is rating. Figure 11 is a heat exchanger process to be simulated. This is a heat exchanger. Okay, B1. You can see stream S1, S3, S2, S4. Figure 13 and figure 12 shows the simulation results. Few results are deleted. Okay. So answer the following 4 questions with accuracy up to 3 digits after decimal point. The question number 1 is the cold fluid outlet stream is. So you need to tell which one is the cold fluid outlet stream. S1, S3, S4 or S2. So these are the stream results. Look at the results carefully. You can see S1, S3, S2 and S4.
So can you go to the previous slide, sir?
Yeah, this is the diagram. So you can note down
Okay,
the
sir.
how they are connected, okay? And these are the temperatures, pressures, molar vapor fraction. The question is the cold fluid
Yes,
outlet
student.
stream is. Which one is the cold fluid outlet stream?
So can you show the temperature?
Yeah.
So, sir, S2 is the outlet stream.
Okay. How?
Yeah, because cold stream inlet temperature is lower while the outlet temperature is higher. That's why. So S1 is the inlet stream, S2 is the outlet stream. So S2 and S4 are the outlet streams, right? So the cold fluid is the one in which the temperature of the stream increases,
Yes.
while in the hot stream the temperature decreases. That's
Yes.
why
Correct.
S2.
So here you can see the temperatures. Okay. So the S1 is 30, S3 is 90, S2 is 44.0383, and S4 is 67.2768. And we can see the configuration S1, S2, S3, and S4. Okay. So S1 and S3 are seams inlet, S2 and S4 seams outlet. So here the S1 and S3, we can see the S1 is the 30, so it's the cold, S3 is the hot stream. You can compare temperature. So the S2 will be the cold fluid outlet stream. The answer is B, S2. Now the missing value indicated by A in figure 12. So you need to find the value A, LMTD. Okay. So this is the figure and these are the data. So let me know the value of A. So you have given a heat exchanger here. Okay. So you need to find the LMTD. These are the stream results. It's important. So take your time and let me know the LMTD. I think the picture is clear to you, right? So temperature is S1 is 30. I think it's clear. S3 is 90. S2 44.0383 and S4
26.32, sir.
67.276. So we have one answer.
26.23, sir.
26.23. Okay. I think you should check your answer again. Let's wait for some other answers. So let me give you the hint regarding LMTD. What is the formula for LMTD?
Delta T2 minus delta T1 divided by ln of delta T2 by delta T1.
Yes. So this is the formula for LMTD. But now important question is what is the delta T2 and delta T1? That's the important thing. So that's the tricky part in this question. So be careful with the delta T2 and delta T1. So what should be the delta T2?
Sir, 44.0383 minus 30.
Okay. No, I think you are confused. So which type of first you need to understand. So which type of heat exchanger you are considering? Because if you read the question, it's not given to you. And you can use counter flow and co-current flow. So which type of heat exchanger you are using? So delta T2 depend on that.
This co-current most probably by looking at the diagram, but I don't know.
Okay, so you are using the co-current. So suppose if we use the co-current heat exchanger, then so it will be like this. So this should be the, suppose if this is TC1, the cold fluid inlet, it will be the TH1, T like HI, TCI. So this is will be the hot fluid inlet. It will be the cold fluid inlet. And then this will be the TC. O, so hot cold fluid outlet, and this will be the THO, hot fluid outlet. So this is for the co-current, sorry, counter current. And if you go for the co-current, then diagram will be like this. Okay. So this will be suppose TCI, and this will be THI, and this will be THO, and this will be TCO. Now it's very important to understand. Now calculate LMTD for both and let me know what are the values. Do we have any answer?
Sir, 1 minute, sir.
Yeah, okay. So if you see for the counter current, so this del T2, del T1 will be this one, and T2 will be this one. Difference between these two temperature. So hot fluid outlet minus cold fluid inlet will be for delta T1 for the counter current, and hot fluid outlet,
Sir,
cold fluid outlet.
26.47, sir.
For which
26.47, sir.
for which type of exchanger?
Uh, one.
Because it will be different for both. Because you see the temperature difference is changed. Okay. So here we are considering
The
both
counter current.
counter current. So what temperature you have taken? What will be the, let me know the value of TCI. Which one is TCI? S1, S2, S3, S4. Which one is TCI?
TCI is
Cold fluid
30
inlet.
degrees Celsius. Yeah, 30
Yeah,
degrees
so
Celsius.
so the S1 is
And
the cold fluid inlet,
yeah,
and the S2 will be the cold fluid outlet. So TCO. S3 is THI, and S4 is THO. So now let me know the delta T2. So delta T2 will be this one, THI minus TCO. THI minus TCO. So it will be delta T2 will be like 90 minus
44.03.
44 point,
0383.
yeah, and T1 will be 67.2768 minus
minus
30.
30.
Now calculate. So calculate delta T2 and T1, then calculate the LMTD. So del T2 minus del T1 upon ln It will be, I think, yeah, ln upon T2 upon T1. Everyone, are you all of you getting the same answer? I think you did some calculation mistake. 26 should not be the answer.
No, sir, I did it for co-current actually. THO minus TC.
Yeah. Okay, so let's see. The answer is 41.4 to 41.5. So it should be like this. Okay. So the LMTD, you can see delta T1 minus T2 upon T1 T2. So for T1 hot fluid in, cold out, and delta T2 hot out, cold in. So you will get the LMTD like 41.47.
Yes,
But
answer is 41.467. It's correct.
yeah, nice. And suppose if you consider it co-current flow, then the LMTD will be 38.76.
38.76.
Now the important question is that, because you have two options, like you can consider co-current or counter-current. It's not clear from the question, because if you read the question carefully, it's given figure 11 is a heat exchanger process to be simulated. Okay, there is nothing mentioned about the co-current and counter-current. Then how will you decide which one you have to use? Because in each case, the answers are different. Anyone have any idea about this?
We will use counter current flow heat exchanger
Why?
because the LMTD value is higher and the area of the heat exchanger used will be less. And in counter current flow, we observe that the thermal stream generated within the heat exchanger is very less in comparison to co-current.
So basically, the counter current is the best design as compared to co-current.
Yes.
Okay. Anything else? Okay, this can be a reason. Any other reason, possibly like in your mind?
So it will be efficient, more efficient than co-current. So it will
Yeah.
help in.
So yeah, we know it's more efficient than. So do you think it's the most efficient one? Because there are multiple heat exchangers. What do you think? Is it the most efficient one?
If we are talking about the most efficient one, it will be shell and type. If we're considering liquids, and if we're considering a fluid, that is air or something, then fin type heat exchanger would be the best.
Yeah. So basically, normally we use the counter current, but also there is. So I think you like some of you
The
have
most
given.
efficient is no, sir. The
Yeah.
most efficient is direct contact, but in direct contact, the miscibility factors come in. So technically speaking, the most efficient will always be direct contact.
Okay. So there's like so many points. Okay. So normally we consider counter current, and also if you just open your Aspen and if you go to the heat exchanger design, so by default, suppose if you don't select the design of flow, then the by default method is the counter current. So this can be also an argument. So if you don't have any options, like which type of flow you are considering, then Aspen is deciding automatically the counter current flow. By default option is the counter current flow. So it can be also, you can think in this direction also. Okay. So normally it should be mentioned in the question, but it's not mentioned. Then so the Aspen is taking the default value. The default value is the counter current. So basically you should know. So suppose if you are not, because in Aspen you can define so many parameters. and some parameters are taking default values if you don't specify them. So in this, it is not specified. So if you didn't specify, then the S1 will consider the default value, and the default value is the counter current flow. Okay, because it's depend on the user. So sometimes we can go for the co-current flow, counter current flow, fins, and so we can do multiple things, but it's not specified in the question. Then we need to go for default value. That's the point. So we consider counter current flow, and LMTD will be 41.47. Now the missing value indicated by B. So what is the value of this B? Now you know the LMTD. Okay. Now let me know the value of B.
So, but we'll require the actual area now. UA delta T. We have 0.5
Can
kV, but we will need a actual exchanger area now.
Why do you need
can
the
we
area?
get the
Because
heat duty? Can we get the heat duty? Acha,
Heat
we have
duty is
sorry.
you need to look carefully. Actually, you need to look carefully.
It is 0.5.
Yeah.
It would be
So
0.5 divided
look
by
carefully.
4.
It's given already, and you know the Q is equals to UA, and you can use the LMTD.
Per kilowatt
Okay.
per Kelvin.
So you have LMTD, you have Q, then you can find the UA.
It is 0.012.
So 0.012, we have one answer.
314.
Yes, sir.
314.
0.01.
2. 0.0.
Okay.
1.589.
Yeah. 1.589.
Sir, it is okay. LMTD is in Kelvin. Okay, sir. 0.012. It's okay.
Okay, 0.012. Okay, nice. So basically, you have given the heat duty. Okay. So Q you have given
Q by
0.5 kilowatt, and you have given the UA. So UA we need to find out. We have know the LMTD. How much? 40.
T1.47.
Yeah, 41.47. So Q is equals to UA and LMTD. Okay, so UA will be Q upon LMTD. So if you divide it 0.5 divided by 41.47, then you will get approx. The answer will be 0.01, and you will get the exact value like this 0.012 dot dot dot. Okay, so this is the answer. So now let me know the missing value of C, required exchanger area.
Can we go back to the B part once? Since it is given that UA the unit should be in kilowatt in Kelvin, won't we change the delta TLMTD from degree Celsius to degree Kelvin? Do we have no, sorry, we don't have to. Yeah,
Okay.
sorry. Yeah, we don't have to. Yeah, I remember. Sorry.
Okay. So what is the because LMTD is the difference. Okay. So basically the temperature difference will doesn't consider it's like if you difference like in
0.01.
the 0 point.
014.
Okay, but the question was a very nice question actually. So let me know the answer. Why did we will not convert the degree into Kelvin? Why?
Because it is
Because the
logarithmic
temperature
mean
difference
temperature
remains the same.
difference. Yeah, it remains the same. So when you
Yes.
when you even change it to Kelvin, you will get the same answer.
So because the difference, we are considering the difference, and the difference in the temperature, like in if they are in degree centigrade, Fahrenheit, in any unit, the difference will always same. Okay, the absolute value is changing, but the difference will not change. Yeah. So what is the missing value indicated by C in figure 12? Required exchanger
0.01.
area.
0.014.
So now you know the value of UA, which is 0.01 dot dot dot. You know the value of U.
Use
So divide this U to this. So you will get the A 0.01 divided by 0.85. So you will get the value again 0.011 dot dot. Okay. This is the answer.
Oh, sir, it is showing approx answer. That's the issue.
Yeah. So next question. So open your Aspen and start solving it. So you have given acetone. You have given the flow rate 1 kilomole per hour, 40-degree temperature, 1 bar pressure. Is being heated by water. 1 kilomole per hour flow rate, 110 degree centigrade temperature, 1 bar pressure. Through a counter current heat exchanger. So it's mentioned here, the counter current heat exchanger. The exchanger duty is 1 kilowatt. Duty is mentioned here, 1 kilowatt. Perform shortcut design calculation. You need to perform a shortcut design calculation. Use ideal property method. The property method is given here. Select it. Then you need to answer the next 3 questions. Question number 1 is, which among the following streams are a mixture of liquid and vapor? Okay, so at 5 minutes, let me know the answer.
It's an MSQ, right?
Sorry,
It's an MSQ, right?
it's an
MSQ.
MSQ. I'm not getting your point.
It's a multiple select question type, right?
Yeah, okay, okay. because it's not mentioned, so just do the calculation, let me know the answer, because it's not mentioned, it's mentioned is oblique R. So it can be.
It is the outlet of acetone and outlet of water.
Okay, so we have one answer. So you mean to say the water outlet?
Yeah, an acetone outlet.
The water outlet and the acetone outlet flow. Okay, anyone else? So we can start the calculation for this. Let me share my screen. Okay, so we have given acetone. So select acetone, then we have given water.
Yes, a water outlet and acetone.
Yeah. So we have given, okay, so have you note down the flow rate? So let me know the flow rate.
1 kilomole per hour, 1 kilomole per
Then
hour.
1 kilomole.
okay, so first we need to select the method, and the method is which one?
Ideal.
Ideal, sir.
So ideal method. Okay, then run it. Go to simulation. Select a heat exchanger. Okay. So be careful with the connections, because one is for this one is for the cold line. This one is for the hot fluid. Okay, be careful with this. Then next. Yeah, so let me know for the cold fluid first. S1.
Oh, acetone.
Temperature
Sorry.
40
40
degrees
degrees.
Celsius.
40-degree temperature.
1 bar.
Okay, 1 bar pressure. Flow rate
1 kmol per hour.
1
1K 1 kilomole per hour. So you can enter flow rate here. Then the next, yeah, for the
110 degrees Celsius per bar.
1110 pressure 1 bar, flow rate.
1 kmol per hour.
Flow rate is also 1K mole per hour. Then click next. So here you can see. So as we discussed earlier,
Let
suppose
it
if I
be
don't,
the weight is.
sorry, yeah.
So we don't
So
have to do anything there.
yeah. So the thing is that,
We have
so
to
suppose,
select specification.
yeah. So you can see you given here the fidelity like shortcut, shell and tube. Okay, so you have given shortcut you need to use, and you have mentioned the counter current. Okay, but suppose in our previous question we have not given which type of flow. So you can see here by default Aspen is considering the counter current. Okay, so you can see here it's already selected. If we change it, then only it will change. By default, it's counter current. So now I think we have given the heat duty or what? So what is the exchange duty?
1 kilowatt.
10 kV.
It's 1 kilowatt. Okay, so all inputs are specified. Run it. Go to the block results. So here you can see the S1, S2, S3, and S4. So the question is, which among the following streams are mixture of liquid and vapor? So you need to check the phases of the mixture. Okay, which among the following stream are mixture? So it means the mixture of liquid and vapor. You need to check the phases of all the stream. So if we check
Vapor
the
fraction, so molar
stream S1 is, you can see only the liquid phase. It's mentioned here. You can also see the vapor fraction. The S2, it's mentioned phase, vapor phase. You can check the vapor fraction. Okay, 1, it's 0. But for stream S3 and S4, nothing written is here. You can see it's not the liquid, not the vapor. It means it's mixed. You can also go to the vapor fraction. You can see the value. It's 0.05 and 0.92. So they are in mixed phase. The answer is S3 and S4. And S3 and S4 represents the outlets. Okay. So which among the following streams? Then the outlet flow of acetone and outlet of water. So B and D are the correct answer. Okay. Any doubt? Okay.
No.
Now the cold flow outlet temperature is.
Sir, it depends on the minimum temperature up.
It's
No, I
55.
think we have already
50,
solved the calculation.
yeah.
From that calculation only you need to tell. The cold flow outlet temperature.
55.7.
Okay. Yeah. 55.7. So you can go to the again stream results. Okay. The outlet flow of, you can check here. So stream S3, the temperature is 55.744. Because we have asked cold flow. Okay. If we asked about the hot flow, then it will be 99.649. The hot flow molar vapor fraction.
0.92.
It's a 0.92023.
Yes, so we can check here the molar vapor fraction. Okay. So for the cold fluid it is 0.051 and for the hot fluid is 0.920. It will be, yeah. So this was the trick. So it was given in the percent. Okay, then you need to type it like this 92. So be careful with these types of things. Okay. The vapor fraction asked in percent. Then we cannot write like 0.92. Okay. So the answer will be 92 to 93. Now it's important. So take 5 minutes and perform sensitivity analysis. It's really important because whenever you model your own systems for your own like industry problems or your like specific problems, then it's very important to analyze. So perform the sensitivity analysis, very specified exchanger heat duty from zero point 0.9 to 1.1 kilowatt with an increment of 0.02 kilowatt. Tabulate calculated heat transfer area and answer the following questions. The first question is the calculated heat transfer area of 940 watt heat duty is. So let me know the area required for the 940 watt heat duty. So go to the sensitivity analysis tool. That will be in the model analysis tools, I think. Specify a variable, you've given data here. You need to vary the heat duty from 0.9 to 1.1 kilowatt. You've given the increment. Okay, 2 more minutes. Anyone? Any answer?
Can we wait a bit more? My Aspen crashed.
Yeah, I'm just waiting for 2 more minutes, 2-3 minutes. So you have given the heat duty variation from 0.9 to 1.1, increment given. Tabulate the heat transfer area. Okay. And you need to vary the exchanger heat duty. Anybody, any answer?
Sir, no, I'm not getting it. Sorry, sir.
Okay. So just note down this data, okay? So let me know. So you can see we have already modeled the system. Okay. So for the analysis, on the left hand side, you can see there is a tool, model analysis tool. Okay, in which we have these options like sensitivity, optimization, constraint, and data fit. So now we are doing the sensitivity analysis. So go to sensitivity. This is the window for the sensitivity analysis. Okay, here you can define a variable which you will change, and you will see the effect of changing of that variable on any other parameter. Okay, and you can tabulate that. So this is the thing we can do. So the purpose of this analysis is like, suppose if you want to optimize something, okay, if you want to see how things are changing, suppose if you want to, so the sensitivity and optimization both are different, but still with the sensitivity we can find a good range, and with that range we can also use the optimization for the perfect optimization. So sensitivity will give you a overall how the things are varying with a particular variation in a particular parameter. Okay, so suppose in our question we have given we need to vary the exchanger heat duty. So what is the current heat duty? We have given a heat duty is 1 kilowatt. Okay, but now our purpose is to see, suppose if I change the heat duty from 0.9 to 1.1, okay, then what will be the effect on the heat transfer area? Because whenever you design a heat exchanger, then area is important, because if your area is high, it means your cost is increasing. Okay, so basically we want to optimize, we want to see the effect. Like suppose if we reduce the heat duty or increase the heat duty like 0.9 to 1.1, and how the area is changing. That's our target. So go to the sensitivity. Okay, click new, enter any ID, you can type any name here, let's say S1. So you defined a S1. Okay, now you have three options: vary, define, and tabulate. So first thing is the vary. So in this you will define a variable that you wanna change. Okay, so which variable we wanna vary here in this question?
Heat duty.
Duty.
Yeah, so it's not the area, it's heat duty. So you want to vary the heat duty. Okay, so click new. So it's one here. Okay, so you can also type a name if you want, let it be one. And what kind of this variable? So if I go to the my flow sheet, so we have like 4 stream connection and one block V1. So in which section we are defining the heat duty? Are we defining the heat duty on the streams, or we defining the heat duty on the block?
Blocks.
Block.
Yeah.
Block.
So if you go to the block, then basically we are defining our duty in the block. So what is the meaning of this? So the variable is the a block variable. Okay, you can see here there are different kind of variables. Suppose if I want to vary the amount of input stream, like input of the cold fluid, then I need to select a stream variable. Okay, but we want to vary the heat duty, then it will be a block variable. So you can see it will have an access a unit operation block variable. So click block variable. Which block? Now we only have one block. Suppose if you are doing the sensitivity analysis of a complete like a system design, then you will have multiple blocks connected. Then you need to select the particular block for which block you want to vary the variable. So here we want to vary the block B1, and B1 is the heat exchanger. Select B1. Now what is the variable? So because we don't know the exact name, but we know, okay, we want to vary the heat exchanger duty. So go to this search criteria. Now type here. So exchanger duty. So you can see here. So we have 4 variables: duty, shell dia. So you can read the description. So this duty specified exchanger heat duty. So it seems reasonable. Select it. So this variable is selected. Okay. Now the unity. So in the question we have given, the unit is like we want to vary the variable in kilowatt range. Okay, for 0.9 to 1.1. And we want to vary it in kilowatt. Okay. Now the manipulated variable limits. So how would you like to vary the variable? So we want to vary it from equidistant.
Equidistant.
Okay, and we have given the start point 0.9, end point 1.1, and we have given the increment. How much?
0.02.
So we have given the
0.0.
increment of 0.02 kilowatt. You need to define the increment. Okay, so now you can see the vary is fully defined. Now click next. It will take you to define. Okay. So now here you need to define a variable. Okay, so it will be like, suppose we have defined this, we want to vary the duty, but now we want to see the results in heat transfer area. We want to tabulate this. So for the tabulation, you need to define another variable that it will show you with the comparison. That will be in the define. It's for the tabulation. Okay. So define a variable. Suppose let's say it's area. You can type any name. Okay. So it's variable area. So what kind of, so now let me know what kind of this variable is. You have four options:
Block variable.
block, stream.
Block.
Yeah. So because the area of the which area? Heat exchanger area. So it will be a block variable. So click block, then type. Again, it's a block variable. Okay. Which block? Block B1 variable. Now search the area. So if you type only area, so you can see the multiple options are there. So be careful. Okay. So we have like area clean, the percentage of excess surface area. Okay. So area calc is a calculated heat transfer area. Select this. So select it. It is variable for the heat transfer area. So you want to see the area in square meter. So unit will be square meter. So it's defined. Now go to tabulate. So now we want a table. So fill variable. So okay, it's come because you have already defined the variable here, area, which you want to tabulate. It's here. So now you have defined everything. Now click run. Okay. So model is converts. Now go to the results. So these are the results for the sensitivity analysis. So the base case value is 0.024 square meter. Okay. This is the summary. So here you can see the variation in heat duty and the area. So the variation is coming in calorie per second, but we defined in kilowatt, but I don't know why it's coming in calorie per second. It should be in
And is
kilowatt.
also the same.
Yeah, but okay, let it be. It's coming in calorie per second. Maybe in the next updated version, it will be in kilowatt. Because we have defined in kilowatt, it should be in kilowatt. But still, we are having the heat duty, okay? And we have the area. So just convert this calorie per second into kilowatt and let me know the answer. The question is the calculated heat transfer area for 940 watt. So convert the 940 watt into calorie per second and use this table and let me know the answer. Okay, so if you change the unit from here actually, okay, on the top side, the English metric, if you click on SI unit and run it, then it will convert into watt. But it should be normally if we define in the kilowatt, then it should be in there actually, but okay, so you can change it from here, from the top side. So now it is in watt. Okay, so now let me know for 940 watt.
0.0226.
Yeah, so for you can see the 940, okay, it's 0.0226724. So this is the answer, 0.02. Okay, so it's better to write up to 3 digits, okay, because you have given 3 digits, so it's better to write 0.022. Okay, now let me know the calculated heat transfer area of 0.025352 square meter is obtained for X watt heat duty. How much watt is required to get this
1040.
area?
1040
Zero?
watts.
1040.
1040 watts.
Okay, so
1040
you can
watts.
directly go to find this area in the table. So this area is, I think, here, and the corresponding duty is 1040. This is the answer, 1040. Okay, so any doubt in this sensitivity analysis is very important actually. So anybody is having any doubt?
No, sir.
Okay, it's really important. You can change multiple variables. Now just let me know if we want to change the flow rate. Okay, just try it. Just try with the changing of the, like this S1, the flow rate of S1. How will you do that? Let me know. So let me know the steps. I want to vary the flow rate. Flow rate of the input cold stream. Let me know. What should I do?
It would be a stream variable, type stream variable.
Type, I have to select a stream variable. Okay.
And we go for mole flow.
No,
S1.
first I need to select the stream.
Yeah.
So you can,
S1.
yeah. So I need to select for S1 stream. Okay.
Mole flow.
Yeah. So select, suppose I want to vary the mole flow. It's mole flow. Okay. So it's now we have unit in kilomole per hour or what?
Yeah, kilomole per.
Okay. So current unit is in kilomole per hour, and the flow rate is, current flow rate are is like 1 kilomole per hour. Okay. So now suppose I want to see what will happen from if I decrease the flow rate 1.5 to 1.5, and the increment should be 0.1. Okay. So now suppose I because I have already defined a variable to vary the heat duty. Now I want to disable that. Now what should I do?
Just click on the active checkbox.
Yeah, so here you can see either you can delete that or you can just click on this button. So now it is deactivated. Okay, it will not run. Only this new variable will run. I'll go to define. Okay, so now what should be here?
It depends on what you want to change.
Okay, so what do you think if we are changing the flow rate? What do you think, the area will vary or not? What is your opinion? Suppose I don't want to change in this variable and I want to see if I vary my flow rate. What do you think? Will your area will change or not?
The area will changes.
Area will change. Okay, let's see. Good to know. Okay, so let's
But
see.
if the heat duty is constant.
So
Yeah.
because now
Yeah.
I have disabled the heat duty and I'm only varying the input flow rate. Now let's see what will be effect on the area. Run it. So if you go to the results,
Yes, sir. As the temperature increases, the area decreases, sir.
okay. So as it's good to see. So if we are changing the flow rate, so the area is changing. But should it be changing or not? What is your opinion? Why it's changing? Theoretically, it should not change. Practically, it should not change. Practically, why it's changing?
No, sir.
And
MCP value increases now because if we increase the area, sir, the MCP value will increase, right? Because the mass flow rate is getting increased. So that's
no,
one way.
this is not the right answer. The thing is that suppose in a company when we have a heat exchanger and we change the flow rate, do you think we can change the area? Once we bought a heat exchanger, can we change the area?
No.
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 But why here area is changing if we are changing the flow rate?
Sir, because no. Let me
Think about it.
Sir,
Think.
sir, if we pass acetone, it will require larger area, sir. So that's one reason to accommodate the fluid.
Just tell me one thing. Suppose I have a company, I bought a heat exchanger, okay, and that heat exchanger is having like 10 square meter area. Now, what do you think? I can change. Can I change that area? I can suppose after 5 years I want to change my input flow rate. So I can change the flow rate because I can change easily because it's just the flow rate. I can change that. But do you think can I change the area of heat exchanger that I bought already?
No.
Sir, we
No,
can't
sir.
change area, but when we increase the flow rate, that liquid will get less time na, as compared to previous case to
No,
heat
no,
up
this
the
area is
another
the
bit
heat
of.
exchanger area. No, no. This area is the your exchanger area, I think.
Here, what is happening is they are fixing the heat duty due to which the temperature
Yes.
we are getting the
So
same temperature. For that reason, we are getting the different area.
you are also
Hmm.
not like you are near the answer. The answer is you see which kind of calculation we are doing. This is the important thing I want to show here. We are doing a shortcut calculation, and the calculation mode is design calculation. Okay, so
Design.
we have not specified the geometry. It's important thing actually. You should consider it because when you have not defined the geometry, you have not defined the parameters, you have defined the heat duty, you have defined the flow rate, then you want to see, okay, this area is the so we have not defined anything. So that everything is like the Aspen is taking the best possible scenarios and giving you the results. So that's the point actually. Okay. So to do the detailed calculation, you need to do the rigorous calculation when we have a fixed design. So it's a shortcut calculation only. That's why it's fixing because we have defined the value heat duty. We are changing the flow rate. So it's taking some internal design, doing some calculation, giving you the best result. That's why the area is changing a little bit. So you need to consider, you need to understand, okay, the effect of the calculations. If you fix the design, the complete design, suppose you fix the cell and tube, you fix all the geometry, everything, then your area will not change. Then what will happen? Suppose, let's talk practically. Suppose I have a heat exchanger. It have a particular area of 100 square meter. Okay. Now, if the flow rate is my inlet flow rate is 100 is the like cold fluid, 100 is the hot fluid. Okay. So with this configuration, I am getting maybe suppose my like I'm getting humidity of maybe 10 kilowatt. Now if I increase this, the flow of cold fluid and the hot fluid will remain same. Suppose it is become 150. Now what will happen? Do area will change? Area will not change. Do it's practically the heat exchanger design is completely, because we have already specified everything. Design is same. Now what will change?
The hot fluid
Fluid
outlet
temperature.
temperature.
Yes, because I think the humidity will also, because if design is specified, the hot temperature is fixed. Okay, so it will be same. The temperature, because you have increased the flow rate, then the outlet temperature will
Decrease.
decrease. Okay, so also maybe humidity will also affected. Okay, because you have changed the flow rate. So, but normally I think you need to do the calculation for it. But the thing is that the point is the your area is same. Area is not changing. You can change the flow rates. That will affect your heat transfer. That will not change the area. But area is changing in our particular problem because we are doing the shortcut calculation. So it's better to go through the case study that professor undertook. I think the last case study is really important for you. This one, design, rating, and simulation of heat exchangers. In this, you will get to know how to design the complete heat exchanger, how to define the many parameters and all. It's good to go through this case study again. Okay, so let's move further. Now, the pressure maintained in the Haber process for ammonia synthesis is
10 bar.
100 bar.
okay. I think it's direct from the case
100
study.
bar, sir.
Okay. Okay, so the answer is 100 bar.
Sir, is it the commercial value or is it the case study value?
Mm, I think the study is dependent on the commercial plants. And I think it's a commercial value also. Yeah, I think the Haber process, I'm not fully aware of this process, but I think for the ammonia synthesis, you require this range of pressure. It can be maybe 110, 120, but in this range actually. So that's why you can see the options. It like 110, 100, and 1000. So they are basically defining a range. So it should be in the 100 bar range. So if you know the range, then maybe the options can be, I think, the like 220, 120, like that also. So I think it's the 100 bar that we choose, but I think it's regarding the range. So figure 1 is the relevant portion of the main flow sheet of Aspen. Okay. Okay, so you can see the figure, you can see the multiple. Okay. So it's the figure 1. This is the figure 1. Okay. This is the figure 2 and figure 3. Figure 2 is the data input palette. So this is data input palette. Okay, this is the data input. And upon completion and simulation run, the results are in figure 3. I think these are the results. They have like, okay, and this is the data input. Okay, so I think that this is typo mistake. So these are the results. These are the inputs, and this is the block. So the block B1 is,
Heater.
so block, you can see there are two streams, S1, S2. Now I have answered block B1 is heater. Please give your reasoning.
You can see the input palette and the output palette. It is written. It's a heater block.
Heat
And
duty
we
is a
can also
minus.
see, and we can also see that the output conditions are the input parameters that are given are that are specified are of a heater.
Okay, yeah. So the question is like, it's not, suppose if I crop the picture and you will not able to see these heater input here, then you need to answer. So you need to see the heat duty. Okay. So we can see it's the temperature is decreasing. It's also, we can see here also it's a heater. Okay, one option. But also we can see the pressure and this duty defined. So based on these data, we can conclude, okay, this the block is the heater and it's doing some heat exchange. That's why the heat duty is there. Okay, it's negative. So the block B1 is, because separator, it cannot be separator, because in separator we are splitting the stream, so there should be the split fraction and all. So it's not a separator, it's not a mixture, because again there is no mixing parameter and all. Not a flash 2. Okay, because why it's not flash 2?
Because we don't have something in a degree of superheating and degree of super cooling in a flash column.
Okay, so that's the one point. But any, like, what is the definition of flash 2? Suppose you don't have these
Flash 2 has two
blocks.
outputs, at least two
Yes.
outputs.
Yes, nice to, yeah, nice to know.
Yes.
So you can see the block, this one actually, it's have only one inlet and one outlet. There are no two output. So it cannot be flash 2. It cannot be a mixture. It cannot be a separator. That's why it's is a heater. Okay. The correct answer is heater. The pressure input at A in figure 3.
1.
1. Everyone, is it 1?
Yes, it's one. Because the
Okay, it's 1.
outlet pressure
Yes.
is 1.01 and pressure drop is 0.
Yes, because pressure drop is 0. Outlet pressure we have given 1.01325 bar. That's 1 atmosphere. So the inlet pressure will be also
The same.
1, the same, because there is no pressure drop. The duty input at B in figure 3, duty input at B.
Minus 20.
Okay, we have an answer minus 20.
Yes, it will be minus 20.
Okay. So it's minus 20 because you can see here it's minus 20,000 watt and here it is asked in kilowatt. You need to convert watt into kilowatt and the answer will be minus 20. The temperature of stream S1 is less than that of stream 2. Options are greater or less.
Stream 1 is less.
Greater.
Okay, so we have a conflict here. Think about it. Let me know the answer. So we have two answers. One is greater and one is less. Which one is the correct?
So heat duty is in minus.
We have a
so,
negative heat duty, which would suggest that
it will be less.
the temperature of S2 would be less than the input. The output
No,
would be less
great.
than the input.
Great.
So if heat duty is negative, then the which one will be greater? S1 or S2?
Input would be greater.
So
Input
feed
will be
S1.
greater.
Yes.
Then the answer will be then greater. Okay.
Yes.
So what is the meaning of, suppose heat duty is negative? What is the meaning of this?
Exothermic heat is getting evolved from the input feed.
Okay. And heat duty is positive. That mean
Means system
Energy is
is
consumed by the reaction.
yes, consuming. It is consuming.
Okay. The answer is greater. So basically, the heat duty is negative. It means that this block is heater. Okay. But what do you think? Now, what is it acting like?
It's acting like cooler.
Acting like a
Yeah.
cooler.
It's acting like a cooler. So basically, heat duty is negative. It means that this block B1 is rejecting this amount of heat, okay, from this stream. So basically, it's cooling this stream by this amount of heat. And if it's positive, it means that this heater is providing or adding this amount of heat to the input stream. So if the heat duty is in positive, then basically we are adding the heat to the stream. It's negative, then we are extracting the heat from the stream. So now it's acting like a cooler. Okay. The pressure of stream S1.
One.
It is the same question.
It's 1. Earlier, I think it was the pressure of S2.
No, sir. It was a value of A, I think.
Yeah, okay. So it was regarding the pressure of the heat exchanger, I think, this heater. At which pressure it's operating.
Yes, it was a block specification.
Yeah. Now it's about the stream. Okay, so it's 1. Okay. So now figure 4 is a relevant portion of the main flow sheet of Aspen plus. Okay, you're given the input pellet. So this is the heat exchanger again. So you can see the streams S1, S2. S1 is inlet, S2 is outlet, S3 is inlet, S4 is outlet. So which one is the hot stream and which one is the cold stream?
S1 is the cold. S1, S2 is the cold. S3, S4 should be the hot.
Yeah. So we can see this from the temperature also, and we know it from our experience with the Aspen. Okay, so this side is the cold and this side is the hot, but it's better to check through the temperatures. The questions, so these are the data. Okay, more data. And the question is the block B1 is.
It's a heat X.
Yeah. So again, the same logic, because in separator 2, the if you see these pellets and all, it should be regarding the separation and all. But here you can see the heat X is written here. Also, you see the inputs required. Okay, so it's based on the heat exchanger. That's heat X block. The answer is heat X. The temperature input at A in figure 6. So here A, what is the temperature?
45.
45.
45. So
Yes.
how do you know it?
Because S4 is the outlet hot.
Yes, S4 is here. You can see the temperature here. It's 45. It's 45. Is. Try to remember it. There are no options.
It is something Exchanger Manufacturing Association. I don't remember the name.
Okay. So the answer is Tubular Exchanger Manufacturer Association or Tubular Exchanger Manufacturers Association. Okay. So both are correct. So it's an important tema. Tubular Exchanger Manufacturer Association. Okay. In the simulation mode of run of HeatX block, the output is based on. input, output, type of exchanger, type of fluid.
Output, input, type of exchanger.
The output temperature.
What are the answer?
No,
Output temperature.
how?
So we have one answer, output temperature. Only one answer, okay? Anybody else think about it? Because I think if you try to remember the class notes, then professor discussed about rating and simulation mode and also design mode. So try to remember the things. It's about the simulation mode.
Type of exchanger.
It's a very interesting question. Try to think and let me know the answer. And maybe like it can be more than one answer. So try to think in that way also. It's not mentioned here that only one option is correct.
They're all four by chance.
All four. Okay, interesting. So we have one answer like all four. But I think type of fluid is you can directly eliminate it. So the D is not an answer. Because we are not, it doesn't, you can choose any fluid. Okay. So yeah, input output you can decide, the exchanger you can decide, but fluid it doesn't depend on that. So you can eliminate type of fluid. So think about the other three. So what about the rating mode? Let me go back to the question number first that today we started. So the question number one was, you have a heat exchanger and you want to know whether the equipment is fit for some desired output performance. Which among the following calculation would you do? And I think
Rating.
one of you told me rating. Okay.
Yes.
So if this is the rating, then what should be answered in that question? So how do like try to link both the question? Try to identify where you are using the rating. So rating,
Rating is used when desired
Type of
output is
exchanger.
so here you have a heat exchanger already. You want to know whether the equipment is fit for some desired output performance.
desired. Yes.
Okay. You are doing the rating calculation. Now try to connect that question to this one.
So it will be based on input.
input and output?
No, output will not be there now because output is what we are
Only input.
calculating.
Yeah,
So how
it
output
could
will
be.
be.
It would be an input and the type of exchanger we use for simulation.
Input is 100% confirm. Then other we have to find.
Okay, so
Yeah, if
we have one answer like the input. So everybody is agree with input. Okay. Now
this type
the
of
discussion is
exchanger,
on output and type of exchanger, and we know that type of fluid is not the answer. So these two are under consideration. Now let me know the
Out,
logics behind the answer. One of you is
suppose
saying the type of exchanger.
yeah, because if we have a silent heat exchanger, we'll have a separate out. We have a different output. If we have a co-current exchanger, we have a different output. If we have a counter current heat exchanger, we'll have a different output. And output itself cannot be the answer.
Our
Yeah, the output itself can be the answer if we are specifying the output itself, but there is no such option as specifying the frequency.
so basically then suppose let me know one thing, as you are saying in your answer that uh, you are changing the heat exchanger each time, right?
Yeah, yeah,
Okay, so it means that you are giving the input,
yeah,
okay, and you are changing the heat exchanger,
yes.
okay, and then you are getting the output automatically.
We are getting different outputs. Yeah.
Okay, you are getting different outputs.
Mm.
So your basically your output is then dependent on the your input
Type,
value and the
yeah,
type
and it is
that you
of
selected.
it. Yes.
Like I think in one question we saw that if we change the counter to current co-current flow, then LMTD will change, and if LMTD will change, then every output will change. Okay, so it seems reasonable to me. Now, what about why this is wrong? Why the output is wrong?
Sir, because if we use the heat block and we change it to simulation mode, then we are unable to specify the outlet temperature of the heat exchanger. It is not giving us the option of specifying it.
Okay, and suppose if I select the rating mode, then what?
Then we are getting
then
the option of specifying it.
we have option there for desired output.
Yeah, right. So the correct answer is input and type of exchanger. Okay, so basically in simulation, we are focused on the input parameters and type of exchanger. So what type of exchanger we are using? So based on this, the output will be calculated. Okay, and in the rating mode, we want to rate our heat exchanger. Okay, so we have output conditions, we have desired output. Now we want to rate it. Like suppose I want a particular outlet temperature. Now for those conditions, I have this heat exchanger. Now I want to rate it. Is my heat exchanger overrated? Is it underrated? Or is it like a best condition? So I want to do that. So then I need to know the output condition. Then this output will be, suppose if I cut the simulation and if I write rating mode, then your answer will be input and output. Okay, because in rating mode you've already fixed the type of exchanger, you have already defined the design, you have everything. But if in the simulation mode you are defining the heat exchanger, okay, you are changing the type of it, you can change that. So output is dependent on the type of heat exchanger. Okay, so these are the questions for today's class, but still we have some time left. Okay, so then I think we can go through the case study.
Can we solve the week 8 assignment part B question?
Yes, yes, sir.
So
We have
which one?
Week 8 assignment part B.
Okay, the part B. So actually I don't know the question, so it's better if you share the question to me already. Like earlier, if you want, suppose guys, if you want to solve the previous assignment question, so there are two things. First, the due date should be over.
yes, it's
Okay,
over.
Okay,
Yeah,
then
it
it's
is.
better if you share that question with me earlier, before the class. Because suppose if I don't have that much time, then I need to go through the question, and also maybe that will not complete. It depends on how many subparts are there. So those are the things. So it's, if you want to, like, in that scenario, it's better to email me at least 3 4 days earlier. Okay. So from next on, like next class onwards, you can do that. Like, and if you have any doubt, share it today. Maybe I will respond through email also in couple of days. So let's go through this case study. Production of cumin. So in this case study, we have to do the cumin has to be synthesized through a Friedel-Crafts alkylation of benzene and propylene. You have given some components, then a parallel undesired reaction between cumin and propylene produces P disopropyl benzene. So you have given the reactions. Okay. The kinetics you have given, the kinetics of the vapor phase isothermal. At the inlet temperature condition, you have given the reactor condition like the isothermal and inlet temperature condition. You've given the reaction rates, the activation energy in given in kilojoule per kilomole. Then you have mentioned like two simulation streams, two simultaneous streams of benzene and a mixture of propylene and butane in 7-3. Each flowing at 400 kilomole per hour at 20 degree and 20 bar. Butane is inert in this reaction. The streams are mixed in heater and heated with a temperature rise of 350 degrees centigrade. One needs to be evaluate the performance of PFR and CSTR. So basically, first we need to compare the performance of if we are using the plug flow reactor and CSTR reactor. To find out the better equipment for the cumin production, the PFR is 5 meter long and 8 centimeter in diameter. It has 350 tubes. So this is the given. So let me open. I think I already have this case study for you guys. So let's open it. Okay. So this is the flow sheet you can see. Okay. So as we given in the question, two input feeds, then we are using a heater to heat it. Then we are using a mixer to mix the streams, and then we are using a duplicator. So the purpose of duplicator, because we have to compare CSTR and the plug flow reactor. Okay, so we want to compare these two. So if you go through the properties, then let's see. So the components you can see we have defined the benzene, propane, cumin, butane, and PDIB. Okay, so you need to search it because you will not find the direct, because the component ID is limited to 8 characters, and it's, you can see the name is very large and you don't remember this name, so it's better to search, use the find button. So you can type this name and you can search it. Okay. Then the methods, we are using the NRTL RK. So I think it's given in the question, NRTL RK property method you have to use. Then go to the simulation. So now it's given in question that two simultaneous streams of benzene and a mixture of propylene in 7:3, each flowing, you have given the flow rates, temperature and pressure. So if I go to the benzene feed, I can see the temperature 20 bar, pressure 20 bar, flow rate. If I go to the other feed, so here also you can see we have entered total flow rate in 7:3. So that's why we are using the mole fraction. So we are using 0.7 and 0.3. Basically 7:3. Then we are using a heater. So we have defined the temperature change 350 degree and the pressure 0. Okay, so pressure drop is 0 and the temperature will be changed by 350 °C. Then we are using a duplicator. So we are duplicating the streams. Then we are using two reactors. For the plug flow reactor, it's given at a specified temperature. It's given in the question actually. You see it carefully, the vapor phase isothermal at the inlet temperature condition. Okay. So reactor with specified temperature, constant at inlet temperature. Configuration, we have given the length and diameter, define that. Number of tubes, I think we have given 350 tubes. Yeah, it has 350 tubes. We have given the tubes. Okay. Then the reaction. So we need to define the reaction. So here we are using the reaction R1. If you go to the reaction R1, then we have two reactions. So first we need to define the stoichiometry. So benzene, propane, making cumene. Okay. And the other one is cumene, propane, and PDA, PB. So use the kinetic model here. Type is kinetic. And the kinetic, so reacting phase, you need to decide the phase, vapor in both case, and define the value of K and E. So we need to look into these equations. Okay. You can see the K value, E value, compare the given equation with these. Okay. So you can enter the values you have not given, like anything like rate basis, then make it default is automatically selected by rate basis. Don't change it. Okay. And in the CSTR conceptual mode, temperature we have given. Okay. Residence time, I think temperature we need to calculate. Yeah. So first we will run only this model, and from this, if you go to the results, then you can see here the temperature and the residence time. So for the CSTR, because we have not given enough information here, then first we use the PFR. From the PFR, we will find the residence time and the temperature, approx temperature. Then we enter those data in the CSTR and then we compare. Okay, so to do that, go to the CSTR results. So you can see the results here. Your heat duty is in this kilowatt, then the minimum temperature, okay, maximum residence time. So these data we are using in the CSTR. So the temperature we are using the same, residence time we are using. Okay, the kinetics we already defined R1, use the same kinetics, run it. So the product and S10, these two streams are from the CSTR and the plug flow reactor. Now go to the results. So we need to compare which one? The PFR out and S10, I think. Okay. So if we compare this PFR out and S10, then you can compare the mole flows. So see because we are focusing on the cumin production. So you see the PFR out, the cumin production is 69.933, and in the CSTR it is 60.8014. So basically the PFR is performing better. Okay. So you can see other details also. The benzene flow is more in this S10. So basically cumin is more here actually. Okay. So with this, we can find out the better equipment. Which one is the better equipment then? The PFR is the better equipment. Now further, for the rigorous calculation, we have given other details. The outlet of the better reactor is, then the question is further is the outlet of better reactor. Then you need to only choose the better reactor, okay? Then you don't need to go for this, the CSTR. Your next things should be connected to the PFR only, because it's given in the question, the outlet of the better reactor. Then you have given multiple parameters. So let me open the other file. Okay, so the outlet of the PFR is further connected. Okay, so first we are using a heater. So basically it's a cooler. You can see the temperature here. So you can see the legends. So the circle is the temperature and the other one is the pentagon is the pressure. The temperature you can see 368 degree to 85 degree. So we are cooling it. It's given in the question. Then we are using a distill block. We are converting the streams. Okay. So you see this is a stream, then other is going here. Then we are further using a separator and we are supplying back. We are again using a heater. So these are all as per the question. Okay. It's again here we are mixing it and we are basically recycling it. So here you can see the cumin production. Okay. So this is the complete model. With the separation, we are also purging. So you need to just follow the guidance given in the question. Okay. So if you go to the inputs, so you can see like we have given the number of stages. Okay. The flux ratio we have given in the question. The duty we have given. Then the streams we have given, like feed stream is above 8 and all. So everything is given in the case study. So you need to follow that. You need to enter the data. Okay, so in this way you can model a complete system and you can analyze many things. Now here, suppose if you want to apply the sensitivity and all, so you can do that. Okay, so suppose you want to maximize the cumin production and you see, okay, I want to decrease the flow of benzene. So you can do that. So just go to the sensitivity, define this parameter as a stream variable, this parameter is stream variable, then vary. So you can play with multiple things. So that's the beauty of Aspen actually. So it's a very good software. You can vary so many things. You can tabulate them. You can easily make curve out of them. So it's a good thing to know. Okay, so explore the Aspen. Try to vary things. Try to optimize the model. Try to do a sensitivity analysis. Connect the stream. See the behavior of the like different variables by changing the different variable. So you can do multiple things. Okay, so I think today we have covered enough. So let me stop sharing. Okay, so a small announcement. I think next week we will not have a class on Sunday. Okay, so the next week our class will be on 2nd of April. So next
Tuesday.
week I'm not available on Sunday, so you will also receive a notification from the NPTEL team, but I'm just informing you prior. So the next class will be on 2nd of April. The time will be same, 7 to 9. 7 to 9.
Okay, sir.
Okay. So, okay, guys. So if you have any doubt regarding your assignment, assignment query, please share that on email. You have my email ID. So I will try to respond as soon as possible. So share that with me. I will look into that. Okay, so enjoy your evening and thank you. Thank you for attending the class. Thank you, everyone.
Thank you, sir.
Thank you for the lecture. Thank you.
Yeah, thank you. Thank you.
Bye.
Bye.